Hey everybody, my name is Kelvin and welcome back to my channel. In this video, we're going to be learning about linked lists. Linked lists are one of the most basic data structures and something you're going to see in a lot of classes, interviews, and real software. A linked list is a chain of nodes where each node stores a value and a reference to the next node, instead of storing everything in one continuous block of memory like a normal Python list. The reason you should know this is that it builds the right intuition for pointer-style data structures and helps you understand trade-offs. Linked lists can be great when you need to insert or remove items by rewiring references, but they're not great for random access because you have to walk from the head to get to a position. In real systems, the same ideas show up in things like queues and stacks, hash table collision chains, certain cache structures, and plenty of places where you're going to be organizing data as nodes connected by links. So in this notebook, we'll build a linked list class step by step, adding a method at a time and running a quick test after each method so you can see the behavior immediately. If you want to follow along while we go through this tutorial, the GitHub repository is linked in the description as usual, and without further ado, let's get started. The first step that we have to do is define our node class structure. This node class is the building block of a linked list. Each node stores a value and an X pointer. If next is none, then that means we've reached the end of the list. The line self.value equals value stores the data, and the line self.next equals next stores the pointer to the next node. We can test this class. We proved three things in this test. First, that a.value prints 10, so values are stored correctly, and second, that a.next points to b because a.next.value should print 20. Third, that b.next is none, showing what the end of a list looks like. And we can see 10, 20, and none, exactly what we'd expect. Now, let's define the linked list class. We keep it minimal so far. We have a head and a size. The head is the first node, and then size tracks how many nodes we have in our linked list. We'll also add a repr function to make printing helpful. In repr, if a toList function exists, we'll show the values. Otherwise, we'll show a generic message. The head starts at none because the list is empty at the start. The same reasoning applies to why we set size equal to 0. We can test this initialization. This test proves the list starts empty. Printing LL should show linked list with a size of 0 because toList doesn't exist yet. LL.head should be none and LL.size should be 0. Now we're going to patch in our first method, the toList function. We want this early because it makes every future test pretty simple, so we can always print ll.toList to see what's inside. Here's how our toList function works. We have values, which is an empty Python list to collect results, and current starts at the head node. While cur is not none, we append cur.value and move cur forward by setting cur equals cur.next. When cur becomes none, we're at the end, and then we return the collected values. And then we append that to our class. We can test it immediately on an empty list. Now we test toList immediately on an empty list. Our test here shows that traversing an empty list is safe and returns an empty list. Now that toList exists, printing LL should show linked list, parentheses, bracket, parentheses. The next method that we're going to be building is a method called append. What does append do? It adds a new value to the end of the list. For a linked list, we either set head if it's empty, or we walk to the last node and attach the new node. Our new node variable here holds the node that we're adding. If self.head is none, the list is empty, so we can set head to the new node, increment the size of the linked list, and return. Otherwise, we start cur at head and walk until cur.next is none, meaning that we've traversed to the last node. Then cur.next equals new node will attach the node for us. and then we increment the size. It's also pretty easy to test. Our test here will prove that append works on an empty list and continues working on a non-empty list. After appending 1, we should see in our linked list 1 and a size of 1. After appending 2 and 3, we should see a linked list representation of 1, 2, and 3 with a size 3. And that's exactly what we see. Our first print statement right here appends 1 to an empty list, so trivially the size is 1. And then if we add 2 and 3 to our existing linked list, then we have a size of 3 linked list with 2 and 3 appended to it. Now, we're going to be putting in prepend. Prepend is like append, but it adds a node to the front. This is one of the fastest linked list operations because we don't need to traverse. We just make the new node point to the current head, and then we update head. Node, value, and next equals self.head creates a node whose next points to the current head. Then head becomes that new node, and then the size increases. Easy enough. Our test here proves prepend puts the value at the front and keeps the chain intact. We expect before 2 and 3, and then after being 1, 2, and 3, and then the size should change from 2 to 3. We have an empty linked list, add 2, add 3. We should get 2 and 3, size of 2, and then we can prepend 1. And then we should get 1, 2, 3, and with a size of 3. Whoops. And that's exactly what we get. Now, let's put in our get function. Linked lists don't have instant random access, so get requires walking from the head. We validate index bounds so we don't walk off the list. If index is 0, the loop runs 0 times and we return head.value. If index is 2, we move forward twice and return that node's value. Simple enough logic. Let's test it. Our test here proves traversal by index works. Our get with index 0 should return 10, and get with an index of 2 should return 30, because we have a 10 appended at index 0, and then we have a 30 appended at index 2. Let's test it. And we'll see that that's exactly what we get. Now, we can also test that invalid indexes raise errors because that's also part of correctness. Can't get an index of 3 because that doesn't exist, nor can we have an index of -1. And our method correctly throws the index error, index out of bounds error. Now we're going to be implementing the find function. This walks through the nodes and returns the index of the first match, or -1 if it's not found. It's a classic linked list pattern. Traverse until you find it, or we hit the end. Again, pretty easy. We set our index to 0 because we're starting at 0, and then we initiate our search at the head. Traverse to the end of the list, incrementing index as we traverse. If we find it, we return the index. If not, we return -1. The purpose of this test here is to return the correct index, and that not found returns -1. We have 5, 6, and 7. If we want to find 6, we should return index of 1, but if we wanted to find 999, that doesn't exist in our linked list, so it should return -1. And we can see that's what we get. Find 6, index 1, find 999, -1, with our linked list of 5, 6, and 7. Our next method is insert, which takes an index and value. This is a key operation because it teaches pointer rewiring. We want insert to support index 0, which is the same as prepend, index equals size, which is effectively the same as an append, and then a middle insert. So we walk to the node before the target index, and then we can rewire the pointers. Prev is the node just before where we want to insert. New node points to prev.next, which is what is used to come after prev. Then prev.next equals new node actually inserts it into the chain, and then finally the size increases. Let's test inserting it. So now we have a linked list with 1, 3, and 4. Say we wanted to insert a 2 at index 1. We should expect a 1, 2, 3, 4, since we're inserting at index 1 with a value of 2. We can see that this is the correct insertion behavior that we're looking for, and we also see that size increments. We can also test the edge cases, insert at 0 and insert at size. So we have a linked list with 2 and 3, size of 2, because we have 2 items in this linked list. And so say we want to insert 1 at index 0, that should be a prepend. Say we wanted to insert 4 at index 2, which should give us 2, 3, and 4. See that both of these work. Our next method is a method called pop front. This removes the head node and returns its value. If the list is empty, the behavior here should raise an error. If not empty, we say the head.value, move head to head.next, decrease the size, and then we return the saved value. The test here is designed to show that the removal at the head works. We expect removed 1, list becomes 2 and 3, and size becomes 2. We have a linked list 1, 2, and 3, and we're going to be running it on this. You can see that this is exactly what we expect. We can also try it on an empty list to test our error behavior. And we can also see that it correctly throws an error with an empty list. Our next method is called pop back, which is basically pop front, but for the back. It removes the last node and returns its value. This is a bit harder than pop front because in a singly linked list, we can't jump to the previous node, but we have to walk. In this case, we have 3 error cases to think about. An empty list, which should give us an error. If it has 1 element, we remove the head and then set head to none. If we have 2 or more, we walk to the second to last, and then we detach the last. If we have 1, again, if we have a size of none, we can't pop from an empty list. If we have a size of 1, we remove the head and then set head to none. And if we have 2 or more, we walk to second last, and then we detach the last. We also decrement the size. Our test here will test our popback method with a linked list of 1, 2, and 3. If we run popback on our linked list, we expect removed 3, and then list becomes 1 and 2, and size becomes 2. And we can see that's the behavior that we expect. We can also test popback on a single element list. The test here proves that removing the only element empties the list, and then after should just be an empty list with a size 0 and head is none, true. And we can see that our popback method works as intended. Our next method that we're going to be implementing is a method called remove value, which takes in value. This removes the first node that matches value. If we remove something, we return true, but if that value doesn't exist, we want to return false. In this method, there are going to be 2 main cases, which is head matches, which we just move the head forward, or middle matches. We walk with prev and cur, and then we skip cur when it matches. If our list is empty, we return false because you can't remove a value from an empty list. If the head is the value itself, then we just get rid of that first node and decrement the size. And then if it's not neither of these first cases, then we traverse the linked list, find the first occurrence, and we remove the pointer to that node. Otherwise, we return false. Now we have a linked list 1, 2, 3, and 2. Here, we should only remove the first two. We can expect 1, 3, and 2 with a size 3, with removed equal to true. As you can see, that's exactly what we expect. 1, 2, 3, and 2 with a size of 4. Successful removal. And now we've removed our first reference to 2. We can also test remove value when the head matches 9, 8, 7 with the head of 9. Say we wanted to remove 9, we should see a list of size 2 and only containing 8 and 7. We can also test remove value when the value is not found. So here we have 1 and 2, remove 999, which obviously isn't in our linked list, and we should get -1. Removed should be false. Our next method here is called remove at, which removes the node at a given index and returns its value. We have 3 cases: invalid index, which should give us an error, index 0, which we reuse our pop front method, and then we have a middle, walk to the node before index and skip to the next node. Again, we can see that in our implementation. If we have an index less than 0, or index is greater than or equal to self.size, then the index is out of bounds. If index is given to be 0, we want to emulate the self.pop front behavior. The important pointer line here is prev.next equals prev.next. Next. This skips the node at the target index, removing it from the chain. We can test remove at immediately in the middle. So we have 10, 20, 30, and 40. Say we wanted to remove index at 2. Index 2 should be 30, and then after that, we should have a linked list of 1, 20, and 40 with a size of 3. Exactly what we expect. And then we can test remove at index 0. 1, 2, and 3. We should expect to see only 2 and 3 left, size of 2. Then we can also test that remove at rejects invalid indexes. 1, 2. We don't have an index of 2, nor do we have an index of -1. Now, let's finish with a LeetCode problem at the end, called reverse linked list. LeetCode will usually give you a head node and ask you to return the new head after reversing. We'll implement a standalone function that does it iteratively, which is the most common interview solution. The idea here is we walk through the list once, flipping the next pointers as we go. We can use 3 pointers here: prev for the part that we've already reversed, cur for the node that we're currently processing, and next node to temporarily save where we're going next. Prev starts at none because once the old head becomes the new tail, it should point to none. Cur starts at head. Next node saves the original next pointer before we overwrite it. Cur.next equals prev, flips the link. Then we advance prev and cur forward. When cur becomes none, then that means we're done, and prev is the new head. And we can test it with a linked list of 1, 2, 3, 4, and 5. After that, we should expect a linked list of 5, 4, 3, 2, and 1. The size remains the same because all we're doing is reversing the list, but before 1, 2, 3, 4, and 5, and then after 5, 4, 3, 2, 1. Next, we also want to make sure we test the edge cases because LeetCode always includes them. We want to test empty list and a single node list. If we test a linked list that was empty before, with a size of 0, it should trivially return an empty list with a size of 0. If we have a single node in our linked list, reversing that would simply just give us the same exact linked list, and we can test that this works. And that's our implementation of the linked list data structure. Our final class should look something like this. We have a node class defined here, and a linked list class with all the methods that we went over. Again, if you want to play around with this class, the GitHub repository is linked in the description. Thanks for watching. If you liked this video and found this useful, please don't forget to like, comment, and subscribe. And I'll see you guys in the next video. Thanks for watching.